This video looks at differentiating functions involving the natural exponential e and log base e, natural logarithms. We're going to use the chain rule to differentiate functions of the form e to the fx and also to differentiate functions of the form natural log of fx. Let's just remind ourselves, back to the first lesson, we looked at exponential functions, functions of the form y equals a to the x, where a took various values. And by investigation, we discovered that there was a value e, an irrational number, which had the same gradient function as the function itself. To 3 decimal places, e is 2.718. And this really important relationship was discovered, that y equals e to the x, which implies that dy dx also equals e to the x. To go beyond this, we use the chain rule. If, for example, we wanted to differentiate y equals e to the minus 2x, we would first look at the inner function, which is the first operation we perform on x. So it's this part here, isn't it? The first thing we do to x is it's minus 2x. So we make u the inner function, which gives us y equals e to the u. If we differentiate the u, we get minus 2. Minus 2x differentiates to minus 2. And if we differentiate y equals e to the u, we get dy du also equals e to the u. And we can now sub back in our substitution, our u equals minus 2x, and make it e to the minus 2x. For the chain rule, we multiply dy du by du dx, where the u is operating as a chaining variable, so we can cancel the du's. It works just like a fraction, and we end up with dy dx. So if we put those two together, we simply get dy dx equals minus 2 e to the minus 2x. Notice that the power stays the same, and the coefficient now in front of the e is actually the derivative of the power. You may eventually, when you get comfortable with these, be able to use that to shortcut. But probably to start with, it's advisable to go through the chain rule step by step to make sure that you understand and that you're accurate in your answering of these type of questions. Okay, so that's what we do with e to the power of a function of x. Let's now have a look at y equals ln x, or in other words, log base e of x. If we go back to basics, we know that if y equals log to the base e of x, then that implies that x equals e to the y. So to get a clue as to how to differentiate y equals ln x, we could just simply look at this and differentiate x equals e to the y. Because we've swapped the x and the y, we're no longer looking at y equals a function of x, we're now looking at x is a function of y. So it's not dy dx we're looking at initially, but dx dy. So because y equals e to the x gives us dy dx equals e to the x, then obviously x equals e to the y would give us dx dy equals e to the y. It's dy dx we want though. Remember, we're trying to differentiate y equals ln x. But dy dx behaves like a fraction. Remember, that's the whole basis of the chain rule. So in other words, if we want dy dx and we've got dx dy, we can just flip it, can't we? Because 1 over dx dy equals dy dx. If you're not quite sure why that works, think of it with a simple fraction like 2/3. 2/3 is the same as 1 divided by 3 over 2. Remember, when we're dividing by a fraction, we can bring the fraction up and multiply, but we have to flip it. So it becomes 1 times 2/3. So it's exactly the same with dy dx equaling 1 over dx dy. So in other words, as dx dy equals e to the y, then dy dx must equal 1 over e to the y. And as we already know that e to the y equals x, we can just make it 1 over x. If you remember back to the first lesson, we actually looked at the function 1 over x and we looked at the area under the curve, didn't we? Different integrals, and we discovered that actually those integrals were natural logarithms. So this is obviously the reverse of that. If 1 over x integrates to ln x, then ln x must differentiate to 1 over x. Okay, so important result. We now know that if y equals ln x, dy dx equals 1 over x. But what about y equals ln of a function of x? Like this example here, ln of x cubed plus 4. Well, it's exactly the same idea as we did with e to the function of x. We use the chain rule, so we substitute the inner function as u, which means we've now got y equals ln u, which is easy to differentiate with respect to u. We know that y equals ln x gives us 1 over x, so y equals ln u will give us 1 over u when we're differentiating with respect to u. And the inner function's straightforward as well. If u equals x cubed plus 4, then du dx is just 3x squared, isn't it? Put them together in the chain rule, and we end up with 1 over x cubed plus 4 times 3x squared. Again, if you look at the pattern here, you can see that what we've got at the bottom is the original inner function, and what we've got at the top is the derivative of the inner function. And again, as you get used to this, you can use these results to do this a lot more quickly. But to start off with, work your way through the chain rule, make sure you understand it. This is also a very important result later when we get to integrate functions like this and use the reverse. Okay, have a go at the quiz now. Make sure that you get credited with watching the video. You have to watch at least 80% of it to do that, and see what marks you can get on the test. If you get a reasonable mark, if you get it more or less all right, then that would suggest that you're ready for the lesson.